All right. So, so we talked about the comments and the operands. We covered the operand part and talked about the registers and immediates and memory and so on. And then we shift to the command part. So today we want to talk more about the command part. There are, as I said last time, there are three types of commands that we have to deal with in Rust 5 and generally in any other Rust-based architecture and ISA. The three groups are the arithmetic or slash the ALU operations, the memory operations, and the control flow operations. We extensively talked about the ALU operations, right? The difference between immediates and non-immediates, the shift, the arithmetic shift, and logical shift, and so on and so forth. I asked the TAs to actually cover some of the basic arithmetics and two's complement things. I think they covered it, part of it on Wednesday, and they're gonna do it again on Friday. So yeah, that could be a good place to kind of like, refresh your mind. And as I said last time, please go and check, either read the book in chapter 2. It has a discussion on all these things, or just follow your old notes or other resources that you think it might be helpful. All right. Any questions about these things so far? All right. So now let's talk about the memory. So I told you that memory has these two main operations, load and store. The load part is the one that you read something off of the memory, and the store part is the part that you provide the address and also provide the data that's been written to the memory. The addressing mode in memory, as I said, is byte addressable. So address inside the memory is byte by byte. So if you say 0, 0, it means it's the first byte. If you say 0, 1, it's the second byte, and so on and so forth. On the CPU side, as I said, we are assuming that things are in 32 bytes, in 32 bits granularity or 4 bytes granularity. So when we read something off of the memory gives 4 bytes altogether. And then if you want to just read 1 byte or 2 bytes or 3 bytes of it instead of the 4 bytes, we need to discard the rest of it and use the rest of it, right? The addressing mode that we are using in memory is what we said the last time, is the displacement, right? The base plus the offset. So we typically don't say go to this specific address. In order to go to the specific address, we usually say this is like the base, and this is the displacement from that base, and that's how we get to that address, okay? So in Rust 5, we usually, for example, say, we use this notation, something like this, that we put the register in parentheses and then put the number outside of it. So this means that whatever value x1 has, that would be our base, and then we're going to add 20 to that to get to that point into the memory. This number could be also negative, which means that whatever x1 has, we're going to go to this opposite direction. We're going to go up to get to that point. So you can both have positive offset and negative offsets. And of course, if you use x0 as your base, then technically your base becomes the beginning of the memory, right? The address 0. So if you don't want to use the base, you use x0 as your base. That would be the beginning of the memory, and everything else would be the offset to that, okay? The whole point of doing the base plus offset is enables us to, first of all, find the addresses that we want much more easier. And the second one gives us much bigger range, because this base, it's a 32-bit number, so you can address anything between 0 to 2 to the power of 31, 32 minus 1, right? So this gives you a huge range of addresses that you can add and you can access in this memory. Versus if you just wanted to do the offset, as I said, the offsets at most can be 12 bits, the way that we designed it in Rust 5. So 2 to the 12 is the most that you can actually address this system, right? And okay. Hopefully it's recording things. Anyway. So That's the idea, right? So the base could be anything between 0 to 2 to the power 32, depending on what register you're using, and then the offset could be anything. So usually, like the big chunk is covered by the base, and then somewhere around that is where you use your offset. Okay. Another important things to remember is the data size that we're gonna get could be different, right? So as I said, the default is that we get things in 4 bytes. And if you remember last time I told you that 32 bits, it means word in RISC-V. But we can also do less than that, of course, right? We can do 2 bytes, which is a half word. We can get just 1 byte. And another thing that we can do is that if we want to read or write things to the memory, we can do it in signed or unsigned way. Okay, so both of them are possibilities. So these are the instructions that we need to care about. So we have 5 different types of loads and 3 different types of stores. On the load part, we have the load bytes, which shows as LB. We have the load half word, which shows as LH. And load word or LW. The default is load word, which when you ask something from the memory, it gives you the 4 bytes. If again, you just want to read the first 2 bytes, you just do the LH. And as you can see on the right side, you see that basically like mathematically what happens is we just read the first 2 bytes from bit 0 to bit 15. That's what we're gonna read, and we're gonna discard the rest. And if he just wants to read 1 byte, then we just read the first, 0 to 7 bytes. So for example, if you have a memory with this, if you want to read this address, use LB with this specific address. What happens in reality is going to read all these 4 for you, but the CPU just gonna like keep this and gonna discard everything else. Okay, so that's what is happening. But the nice thing is that on the programming side, on the assembly side, what you will see is that you just read 1 byte and the rest is 0. Say it again. Oh, the immediates. So the question is, how long are the immediates? So remember, whatever length that the immediates has, we have to sign extend it to 32 bits. So we are always assuming that when we are doing this calculation, our immediates are 32 bits. What they originally are, later on I'm going to show you the size of the immediates. They can change from 12 bits to 20 bits in RISC-V. Yeah, so the question is, all the memory instructions have a certain width for immediate, and the answer is yes. We will show you the tables of all those things very soon. Okay, and then another thing that we have is we have the unsigned version of this as well. We have the unsigned version of load bytes, and we also have the unsigned version of load half bytes. Load half word, which means that whatever we're gonna read, we're gonna just read the 0 extent of that, because remember, we're gonna read like 8 bits data, right? And the question is, if we want to write this, for example, 8-bit data on this load byte, what should I do with the rest of the bits? Because I want to write this into a 32-bit register, right? So if I do the regular load bytes or load half word, we're gonna sign extend it and write it to that part of the register. But if you do the unsigned version, we're just gonna 0 extend it. So basically, we're gonna just read this 8 bits, and the rest gonna be just filled with all zeros, even if that this last byte, the signed bit is 1. Okay, so that's the difference between these 2 instructions here and these 2 instructions here. And of course, we don't have load word unsigned, because we're assuming that, when you're doing the load word, you're loading the entire 32 bits, right? So whether you like it or not, you're going to get the sign as well. You can treat it as unsigned, that's fine, but you're going to get the whole 32 bits together. So the question is load word and half word doesn't get 2 bytes or 4 bytes together. It's issues multiple load bytes. That's the question, right? No, it's actually the other way around. So we always do load word and then ignore the rest. So in order to make things faster, whenever we want to read something from the memory, we always read 4 bytes. And then if we don't need it, we're going to discard the rest because it's more likely that you need more data than less data. And reading things is much more faster that way. Oh, for the load byte, you mean? So load half. So the question is, so the load half word is like, if you look at the memory like this, and let's say you have line 0, 1, 2, and 3, load half word says I'm gonna just keep these first two lines. Okay, I'm still gonna read all the 4s, but I'm just gonna say that I don't care about these 2. I'm just gonna keep these 2. If you're confused, if you look at the right side, you actually will see that this is like how we are treating this. So think about reading from memory as this M array M, right? Which the index to that array is RS plus the immediate, which is the address. And what the load byte does is just saying that, oh, I'm going to just read from 0 to 7. Like, if each individual, element in that array is just 1 bit, then what we are doing with load byte is saying that from 0 to 7, which is 1 byte, I'm going to read that. And for half is 0 to 15, and so on and so forth. Okay? Yes. So the question is that the first one just sign extend. There's no way to get multiple bytes in this. So that's the half word and word, right? So if you want to get multiple different byte, you want to copy of the same byte? Is that what you're looking for? So, if you want to read from very different spots, yeah, there is no way to. You can only read consecutive 4 bytes together. And if things are far apart from each other, then you have to issue multiple loads. So the question is, would you get them all in one register? Yeah. I mean, you have to write your own logic to do that. Think about it as the same way that you want to concatenate things together. It's the same story. So you read 1 byte, maybe shift it to the left, read the second byte, shift it to the left, and so on. So the question is then, would it sign extend and overwrite the previous? Yes, if you use the same register. So what you should do is you have a separate register for your concatenation and one register for reading. So you read things into one register, and then you have another one that's kind of like, put these puzzles together. Cool. So now let's look at the stored ones. Stored ones, as I said, it's when we are providing data to the memory. As you can see, the big difference is it doesn't have RD anymore. It has RS1 and RS2. And the way it works is that the RS2 is the one is the data, and RS1 is still doing the same for the addressing. Remember, we still need the base plus offset, right? So base plus offset is still our way that we are addressing the memory, and this base is still RS1, similar to the load. But another thing that we need to add is the data to the memory, right? And this data is coming from RS2 this time. Okay, so the difference is these two looks very similar, but two things that's kind of confusing. First of all, RS1 in this case is on the left side, and the second thing is that the RD here is now RS2, which means that in load we are writing things to RD. In store we are writing from RS2 to the memory. Okay, so that's the difference between these two. And if you're confused of how we are using it, take a look at here to kind of like, understand what is the use case for RS1 and what's the use case for RS2. And also pay a lot of attention to the ordering of these. So RS1 is on the left and RS2 is on the right. Okay, don't mix things up. Does that make sense? And similar to, before answering your question, similar to loads, we can have a store byte. So we can just write 1 byte to the memory or half words to the memory, okay? And whether or not this is a sign extender or not, that's your decision because you're the one who's providing this data to the memory. If you think this is sign, it will be written as sign. If it's not sign, it will be treated as unsigned. Question? Yes, the question is if you'd use the SB and you decide, say, I want to write into 0x00, what will happen to 0x1 and 2 and so on? The answer is they won't be changed. So it's safe to assume that nothing in this part and so on will be changed. Okay? Any other questions?
You said the memory is specific, according to the time period, which also
So the question is that there is a confusion between the thing that I said last time that memory is 32-bit versus that I said that memory is byte addressable. So it's different perspective. So when I say memory is 32 bits, I'm talking from the CPU point of view. So whatever CPU sees, it thinks that by default memory is 32-bit. But inside the memory, what is happening is that memory is byte by byte, okay? And the reason, again, is it's like thinking about that if I want to go to my office, it makes sense to bring all the books that I think I might need because the overhead of going to my office and coming back is large. So what I would do is that I'm going to bring things anyway. And if in most of the case I'm going to use those things, it means that I'm not wasting things. And if like in 1% of the time or 2% of the time I'm going to waste things, that's fine. Versus if I just bring one book and then when I'm come back and say, oh, I need another book as well, and I have to go again and again and again, that's the waste. And you will see, especially about memory, since memory is the major bottleneck in terms of performance, we just try to bring as much as we can in every try. So it could be even bigger than 32-bit, for example. When we are reading from cache, for example, we are reading in 64-byte chunks, even though we might just need 1 byte. So we are sacrificing 64 of that blocks by just reading 1. So that's the story. What do you mean by larger one? Yeah, it's the same thing. So the question is that memory is the large array that we are talking about. Yes. So as you can see here, we are talking about M, which is this big array for us. No. So this question is the large memory consists of registers? No, the registers are inside the processor. So inside the CPU. So think about this as this architecture like this, which we have a CPU, there's a tiny bit of kind of like memory inside this, which we call register, okay? And then there is a bigger, very much bigger memory here, which has many lines. So here we are talking about millions of lines. Here we're talking about 32 lines, okay? So these are our registers, our X0 to X31 here. And here is our memory. So if you want to issue load and store, it means that we are going here. If you are using the regular X1, X2, it basically what happens is that we are going here. Okay? Why is what? Why the base is register? Because so register, think about it as our temporary variables. So what we do with registers is like if you're writing a program and you want to do things with your variables, you use registers. So it's kind of like the same use case for it. You have to store your information somewhere, right? In your hardware. And that somewhere is your register. It's your temporary location, which is very, very fast, but it's very, very limited. So you use that in order to like move things around. So it's kind of like, again, back into the analogy, think about it as this desk and your library. So in your library, you have lots of books, but in your desk, you can hold maybe like 5 to 8 books at most, right? In this big register, big table. So this table is your register. So you can bring things here, but temporarily using it. And after you're done with it, you put it back into your library. Yes. So the question is the address of that memory. Yeah. You think about it. Whenever you want to read something from the memory, you have to know where it is, and you need that address. And again, it's your responsibility as the programmer to know where that address is. Yeah, the question is when you're doing load, when you do a store, not load. When you do a store word, some data 00, it will write to 00, 01, 02, 03, this 4. Yes. Yes, if you load word from 00, it will also read from 00, 01, 02, 03. It goes downwards, basically. You can alternatively go back up, but it's easier to go downwards. All right. Any other questions from the memory part? I think we talked enough. So yeah, this is the memory part. Just pay attention to the 0 extent versus the sign extent. Pay attention to the RS2 and RS1 for the stores. And that's kind of it for the memory. Okay. We're gonna talk a lot about memory later on, like, because inside the memory there's also hierarchical memory. So it's not just one big giant array. It's actually within arrays there are arrays. So we will talk more about that. All right. But for now, just think about memory as this giant storage area that needs an address to read things, and the CPU just treat it that way. Okay. So now let's talk about the control flow. So the big thing before understanding the control flow, and in order to understand how computers work, is that we generally, all of these systems that we use, including your laptops, the tablets and cell phones and all those things, follow this format called store program computers. Okay. So what the store program computer means is that we are treating the instructions, the program, as part of the data as well. Okay. So what will happen is that we have our like C program, and then we get our ASM program. And then later on, I'm going to show you how we get to the machine code, which is just basically a list of zeros and ones. Okay. Once we have these zeros and ones, the question is, okay, what should we do with this? What we're going to do with this is that we're going to put this into the same memory that I just described to you. Okay. What we're going to do is that we're going to say that, for example, this first quarter of the memory is for the instructions. And I'm going to just load these instructions that I'm going to use into this part of the memory. Okay. And what happens is that when the processor wants to execute things, it's going to go through that memory line by line, and it's going to bring that instruction and it's going to decode that instruction, which we're going to talk about how, and it's going to execute that instruction. Okay. And the rest of the memory is basically your data. Okay. So the rest of the same memory is where you store your temporary data, your sensor values, your sums, your calculations, and all those things. But in terms of memory, like, from memory perspective, there is no difference between instructions and data. All of them are just a bunch of zeros and ones. And when we are reading things, there is no difference between instructions and data for us. Okay. And we call this store program format. Okay. Which basically what it means is that instruction and memory and data does not have any difference for us. There are other alternatives which we may get into later on in the course, but this is the overwhelming majority of devices and architectures, including all the laptops that you're using and all the cell phones that you're using this format, which is also named after this prominent researcher called von Neumann. So we call it von Neumann machines. All right. Any questions about the store program? Okay, so now we understand this. Let's actually see then what is control flow and how does this work. Essentially, since I told you that, we have this memory, which basically line by line, we're going to store program. And by the way, we said that instructions in RISC-V are 32 bits, which means that every instruction occupies 4 of these lines in the memory. Okay, same story that each line is 1 byte and all those things also applies here. Okay, so our instruction should be broken down into bytes and it's going to be written into this memory, which if you have like 0 to 7, it's going to be written in here. From 8-bit 8 to 15, it's going to be written in here, and so on and so forth. Okay, so the lower address gets lower data, which we call it little Indian, which I'm going to get into later. But just for now, think about it. That's if you have a 32-bit instruction, you're going to break it down into bytes and write it into consecutive lines of memory. Okay, so in order to understand and kind of like follow that, what happens, like how the CPU knows where to go and how to read things. CPU use this special register called the program counter or the PC register. So this is different from that 32 registers that we have. It's the same format, it's the register, but it's not the same as all those 32 things that we said, the X0 to X31. Okay, so we call this PC. And this PC will be initialized by the system software, by the operating system when we want to run a program. So what happens is that the operating system going to say that, you know what, I'm going to use this program that you have written, and I'm going to put this maybe in this part of the memory. And the beginning address of this would be initialized to PC. So maybe this address is, I don't know, some random number, some 1123 or whatever number this is. This is the beginning of my program. And the rest of my program is just consecutive in the same part of the memory. It's just one block, one after another are my instructions. So what the operating system will do is that it's going to say that, oh, your base is going to be written into this PC. Okay. And afterwards, what I do is I read this instruction. By I mean the CPU. I will read these instructions one by one. I'm going to read one chunk. I'm going to issue a load and read one instruction. The first instruction, I'm going to execute it. And then I'm going to issue another load in another consecutive line of the memory and do the next. And the important thing is that, as I said, since the lines in memory are byte by byte, so the first PC going to be instruction number 1. The next instruction would be where? It's going to be in PC plus 4. Okay. Why 4? Anybody? The instructions are 4 bytes, right? So once you read PC, you get the first instruction. The next instruction is not in PC plus 1. The next instruction is PC plus 4 because 4 of them together creates your instruction. Okay. So on the CPU side, we do plus 4, plus 4, plus 4 in order to go to the next instruction and next instruction and next instruction. Okay. So in our 32 word of RISC-V, things are on the processor side should be increment by 4 when we are talking about the PC. Okay. So and if you're, for example, switching to 16-bit format or 64-bit format, then that number changes, right? For 16 format, it's going to be PC plus 2. On the 64-bit format, it's going to be PC plus 8, right? But for now, we don't care about those things. Just keep in mind that the reason that we are doing PC plus 4 is that we're going to want to go to the next instruction. Our next instruction is 4 byte away from our current instruction. Does that make sense? Any questions? It goes down. So the question is, the instruction starts at 123 and it goes down, and the answer is yes. The question is, what goes above them? Previous programs. Yeah. But also, like, whether it goes up or down is architectural dependent. So there are things that goes up and there are things that goes down. So that's really not a specific reason that's why it's going up or going down. It's just a decision that the designer makes. And usually what happens is that because of the backward compatibility, they don't change these things. So like Intel, go down or go up, whatever it is, it always stays the same. And then once you, so we're not going to talk about like, how we structure memory and all those things. This is like relevant to an operating system course. But typically your memory is not, as I said, it's not just one consecutive segment. You usually have multiple segments within each. So we create this notion of what's called a process. And each process has its multiple different segments, like data segment, it has code segment, it has stack, it has heaps, and all those things. So what happens is that your operating system will gonna block part of your memory and say that, oh, this is for process number 1. And then I'm gonna block the rest of the memory, and this is process number 2 and 3. And within this, we have different sections. We have data section, instruction section. But again, these are not relevant to this course. This is the operating system course that talks extensively about these things. For now, just imagine that what happens is your operating system just takes your program, which is list of zeros and ones all together, and then just going to put it into somewhere in the memory, somewhere random, which we don't know. All we know that where is the beginning, and that's all we know. And that's all that matters for us, because that number is on PC, and then the PC is going to just increment by factor of, by number of 4, 4, 4, until we reach to the end. Does the instruction encode the register that's going to be used? You mean like RS1 and RS2 and those things? Yeah, so it's, the question is like, does add instruction specifies RS1? Yes, and that's the whole point of the instruction. So we're gonna, very soon, we're gonna get into the actual, machine code, and you will see that, for example, if you use X1 versus X2, the machine code is different. And that's why we're going to interpret which register is it going to use. You had a question here?
Last lecture, I think you mentioned that there were 32 registers we can work with, but sometimes you said 34.
No, I didn't say 34.
Okay.
Maybe I just, yeah. So the question is that last time I said there are 32 registers to work with, and sometimes I said 34. That was just a mispronunciation. So yeah, it's always 32. No, as I said, PC is a separate register. So the question was, is PC included in that 32? No. So it has a separate name, literally PC. Okay? And then the interesting thing about PC is that for some ISAs, PC is visible to the software developer, so you can actually read and write things to the PC. But in some others, PC is not visible. So it's only the hardware is the one that can write things to. But that's, again, it's a minor detail that's not completely relevant. Any other questions? Cool. All right, so let's continue. So question is, what is control flow and why we need it, right? So at the basic level, as I said, we can think about memory as this linear version, which we have our instruction blocks. And I'm going to say, oh, I'm going to read this, then +4 next instruction, +4 next instruction, and then like at some point I'm going to reach to the end of the program, and the operating system going to take over and then move on to the next application, right? So if things are just linear, our story is kind of like, okay and done. We don't need extra things. But unfortunately, we have conditions, we have function calls, we have returns, and we have all these things. And what this does to our instruction is that it creates nonlinearity, right? So think about like something like if then else, right? So if then else, what it does is that it says, oh, check this condition here. If it's true, then run this series of instructions. If it's not true, then jump from here and go here and run these things, okay? And if you want to create a linear format of this, we're going to translate this into a series of instructions, and we're going to put these things into our memory. But the reality is that if this condition is true, maybe we have to, execute these 3 instructions and then not these other instructions, okay? So there is notion of jumping and there is a notion of branching in our code. So we need this instruction called control flow instructions, which basically manipulates the use of PC. And remember, in order to jump from some instruction, all we need to do is changing the PC, right? So for example, let's say we have 3 instructions and our current PC is pointing to this instruction, okay? So we are reading this instruction and we're going to execute this instruction. That's great. And let's say this is an if instruction, says that, jump from this instruction. So what I need to do is that instead of doing PC plus 4, right, all I need to do is doing PC plus 8. So I intentionally change from 4 to 8, and that means that this instruction here going to be skipped, right? Because the hardware doesn't know which instruction is which. The only thing it knows is that tell me what PC is. I'm going to go to the memory and we're going to read that. And if I tell the hardware that the PC is not PC plus 4, it's PC plus 12 or whatever other number, the hardware going to go and read that number, right? So we're going to skip as many as instruction that we want by just changing the PC, by just manipulating the PC. And then we can go back and we can go forward. We can do all those things that we want. We can jump into another completely different part of the memory if you want to. For example, let's say there's a function call that we want to jump to somewhere else. We can do all those things by just changing the PC, okay? So that's the instructions that manipulates the PC for us. It's called control flow instructions. Does that make sense? Any questions? Cool. So let's see what those are. So the first one, which you already probably know, is the jump instruction. And the biggest question about the jump instruction is jumping to where, right? We need what's called a destination. And in order to jump to whatever we want, the way that we address this is we call it PC relative, okay? So what does that mean? It means that we always assume that our base is the PC. Remember I told you that in memory, we think that our base is RS1. For jump instruction, we assume that RS1 is PC, okay? So we don't need to provide RS1 to the instruction. We just provide the offset. And that offset automatically gonna take the base from the PC and just adds to it, okay? So we never jump to specific location. We always jump relative to the PC, okay? We can jump PC minus something or PC plus something. So if you have some instruction like, jump to like 100, it means that whatever PC is right now, just add 100 to it and the next instruction is going to be that, okay? So that's the trick that we're going to use in jump instruction. So the addressing mode for jump is PC relative, okay? It's still base plus offset. The only difference is that our base is our PC, not registers. We cannot change that, okay? Any questions? So the question is that if we have a jump instruction, then there is no addressing, there is no other base that we can use. And the answer to that is no. But we have another instruction called jump R, which jump register, which I'm going to get to into next 2 slides. And that one is the one that's replace PC with your register if you really want to. So the question is that if we are adding PC plus 4 after every single instruction, should we do that for jump instruction or not? And what happens is that we're going to just show this how it's actually being implemented in hardware. But think about it as some sort of like a multiplexer, a decision that either says, oh, either go to PC plus 4 or go to this destination I'm telling you. Okay? And what happens is we need a mechanism to make a decision whether we have to do PC plus 4 or whether we have to do jump, which we're going to get to soon. But what happens is that by default, you do PC plus 4 and you always create that PC plus 4. But when you get to the jump, you say, oh, ignore that PC plus 4, go to this place that I'm telling you. The question is that if the PC gets updated after the jump, for now, think about instruction by instruction, and things happen simultaneously for each instruction, which means that if I have a jump, it means that if I want to execute the next instruction already has the updated jump, updated PC. In reality, this happens into multiple clock cycles, which when we are discussing the actual microarchitecture and the pipeline, you will see that when the PC is actually updating, it's happening somewhere during the execution of that instruction. But the exact timing, we need to understand the data path, we need to understand the pipeline stages, and once we understand those things, you will see where the PCs actually get updated. But you are in the right track. Yeah. So the question is that the jump instruction gives you the address of where to jump to, whether rather than giving you telling you whether to jump or not, right? Yes. Or yeah. So there is a big difference between what's called a jump instruction and what's called a branch instruction. The difference between these two is that the branch is not always jumping. So branch is a specific type of jump, which first check a condition, and if that condition is true, then it will jump. But jump always change your PC. Okay, so the jump is just saying, it's like a, think about like, you know, a best use case for jump is a call function, right? So for example, in your code, you have like, you know, call this function to do this. That's exactly where you want to use jump, because your beginning of the address of your function is somewhere else into your memory. So you want to change your PC to point to that beginning of that function, okay? Versus your branch instructions is when you're using your conditions. So like if then else's, for loops, while loops, and all those things, they all use some form of branch, because you don't know whether you want to jump or not. If the condition is true, you want to jump. If the condition is not true, you don't want to jump. So that's the big difference between these two, okay? And this is specific to REST 5. There is this specific instruction which called jump and link, which they call it GL. So GL, what it does is that still the GA part, the JA part is still the same jump that, the J part is the same jump that that just described. This linking part is basically saying that for each jump, there should be a return. We have to come back at some point to where we are, usually when we are writing our program, right? Whenever we call a function, we need to return at some point to next instruction after that, right? So for example, let's say we have this instruction, then we have call this function, I don't know, foo, right? And what happens is that we're going to go jump to this part, execute foo, and at some point we have to jump back exactly to the next instruction after this, right? So this jump and link makes our life much more easier, because it says that whenever I see a jump, I'm going to record this address into a register, into my RD, okay? So whatever PC currently is, the linking part says write PC plus 4 into RD. Again, why do we need that? Because once we get to the return part, the return is nothing but another jump. And where it does to jump to, jumps back to wherever we called the instruction from. And we don't save PC to RD, because if we jump back to the call, again, we have to do the call. So it's kind of like, you know, an infinite loop of calling and returning and calling and returning. What we do is that we save PC plus 4, the next instruction after that call, into our linking part. And that means that whenever we're done with that, whenever we execute the return, which is another jump, we're going to jump back to where we were before. Okay? There are some questions. So the question is that if your function calls another function, what happens? And what we will talk about the calling convention and what happens. What you need to do is that you need to store things into separate registers. What happens is that usually the operating system take care of this in stack. So we really don't save this into a register. We first save it into a register, but we write it into a stack, which is a memory. But for now, just think about it as we can only, whenever, if you have multiple jumps within each other, we have to write it into a separate register. And if you have like 32 registers or 31 registers, we can only do 31 of these. We cannot do more, which is all of these different hardware has some number of limited number of these within calls. What, you have one question here, another question? Good. Cool. And another question is, what if we don't need link? I just don't want to link. There's no return. I don't want to return. You still need to execute jump on link, but what you can do is this trick that people use and use RD equal to X0. Okay. So remember I told you that you cannot write things to X0. So when I say that my destination register is X0, I'm implicitly saying that this value I don't care about, I don't need to link it, okay? So if you want to jump without really linking something, use jump and link with X0, okay? And the same story for anything else that you want to ignore. If you want to ignore something, use your X0 as your destination register, okay? There is no, so the question is that is there no actual jump instruction? No, do you actually see the list of instruction here? We have what's called JAL and JAL-R, which JAL is jump and link, and JAL-R is jump and link register. And then we have a bunch of different branch instructions, but we don't have the specific jump instruction because there is no point of having a specific jump instruction, because jump instruction is nothing but JAL using X0. Okay, so if you use your destination with L, it's the same thing. Okay, so what's the difference between JAL and JAL-R? The difference is, if you look at here, so what it does is that the linking part is exactly the same. So both of them, the RD gets PC plus 4. So if you see the RD here gets PC plus 4, the RD here also gets PC plus 4. The difference between these two is that the JAL takes whatever value that we have here in label, versus the JAL-R going to use this RS1 as the base. So the difference is that in JAL, we're going to assume that PC is our base. In JAL-R, we're going to assume that RS1 is our base. Okay, this is for function pointers and all the pointers that we're going to use in our like C and C++ programs and all those things. So if you want to do fancy things, we use JAL-R because we need to do indirect jumps. Versus the direct jumps is when we are using things like, for loops or if switch cases and all those things. Okay, so there is a reason that we need JAL-R. Questions? Yes, the question is for JAL and branch equals, the label is an immediate, and that is correct. And the interesting thing is about the immediate is, let me see if I actually, yeah. Oh, no. But it doesn't work. Oh, okay. Okay. So the difference is that if you read that thing that I wrote in the bottom of this slide, it says that label is basically PC plus immediate. Okay. So what does that mean is that if this label wants to be PC, if let's say our PC right now is 0x100, or actually let me do it in binary in decimal so to make things easier. So let's say our PC is equal to 100, okay? And for some reason, we want to jump to somewhere that is like 8 bytes behind. So our immediate should be 8, but our label says that our label is equal to 108, okay? So there is a difference between what is the label and what is the immediate. The immediate is the value that we add to the PC in order to get to that label, okay? So the label is 108, but our immediate is 8 because our immediate is the offset to the PC. Whatever the PC value is, you have to add that to your offset in order to get to that label. Does that make sense? So the question is that when we are writing the assembly, we write the label. You can write both. You can do both. In order to make your life easier, you can write the label. So basically, if you recall when you are writing your assembly, probably for your ARM or something like that, what you would do is you say like label loop, colon, and then do some instruction here, right? And then at some point, either on the top or on the bottom, you say, for example, jalr or jal, and you do, for example, jal, and what you do, sorry, you do jal, and what you do x0, for example. Let's say we don't care about linking, and we're gonna just say loop. And the compiler will understand that it means that we want to go to that label. In reality, what happens is that this value, in order to calculate this value, we have to see what is the PC value of this. We have to see how many bytes is the difference between here to here. Assuming that each instruction is 4 bytes, we have to calculate that, and we have to find the offset to satisfy this distance. Okay, so our immediate is actually the distance between these two. Okay, it's this. The loop, though, is just say jump there. So the loop is just this fancy things that the compiler helps you to understand your program. You don't have to manually calculate, oh, what is the offset for this instruction and what is the offset for that instruction. But when you're actually creating the machine code for this, the immediate has to be calculated. Okay. The good news is that all these things are automated, right? But in homework, for example, we're going to ask you to give us the immediate for this to understand this concept. And the immediate could be negative or could be positive. So you can either go up or you can go down in your program. Either of those two works. There was a question there. So the question is that when you're using jal x10, what does plus some immediate, what does that mean, right? So if you look at here, this is basically your guideline to understand these things. So when we have jal and RD, for example, is x10, and your label is x10, and your label is some label or some value, what does that mean is that if you look at here, it means that RD gets PC plus 4. So in this case, x10 gets PC plus 4, and your PC gonna get the label. If you want to jump to the address that x10 points to, then you have to use jalr and then use rs1 like this. Okay, so you do jalr and whatever register you want to link to, let's say like x11 in this case. And then, as I said, we usually use this format of putting the offset outside and putting the register number inside. So this means that whatever value x10 has, add 10 to it and update my PC with that number. And also does another additional thing, which is whatever PC currently is before updating this, add 4 to it and store that value into x11. Okay, does multiple things at the same time, but if you actually follow here, you will see all those things. Like we do PC plus 4, we record it into RD, then we update the PC with whatever value that there is in RS plus offset, and we're going to jump to that point. Okay. Yes, the question is, instead of label, we can put immediate value. Yes, and the compiler usually understand that. But when you're putting your immediate value, just be careful because you have to calculate that immediate value correctly. To make your life easier, you can just put the label inside your assembly code, say loop or my label or whatever name you want to name it. And compiler is very intelligent that actually recognize that label and find the correct offset for it and all those things. But in your homework, for example, we're going to ask you to calculate that offset for us. Okay? Okay, so there is one question here that why are we doing this here? So we're not actually saying that 0 to 31, we are saying 1 to 31, and then for some weird reason, we are concatenating this with 0. This also asks in campus wire. So first of all, it's a design decision. There is no specific fundamental reason for it. And the design decision is two things. One is doing this help us in two ways. Number one is it basically implicitly say that we cannot jump into odd values of memory. And that helps us a little bit because in order to read things from memory, simpler options helps simplify the hardware. When you're actually designing the hardware and describing that for you, you will see that why this matters. So basically, this prevents you to jumping to odd part of your memory, and that simplifies hardware in some sense. The second thing is that if you want to just do 16-bit instructions, again, you don't need to change things. We can just, again, jump into just 2 bytes increments. And another thing that this RISC-V people designed was they wanted to use this least significant bit for some flags. So you can actually store some additional information in your JALR. We're not going to cover that, but you think about this as you can basically add additional information into your JALR instruction. Does that make sense? Any other questions? Okay, and then we have a bunch of branch instructions, which all these branch instructions, as you can see, is doing one basic thing. It's gonna check whether a condition that we want is happening between RS1 and RS2. As you can see, we have 6 different type of branches. We have branch equal, which basically compare whether RS1 is equal to RS2. We have not equal, less than, greater, equal, less than unsigned, and greater, equal, unsigned. Okay, so you can actually, it's simple, the math behind all of that. And what happens here is that, as you can see, the difference between branch and jump is that, first of all, there is no linking. So the whole linking part is only for jump. So there is no linking with branch. But for branch, you have 2 options. You either get the labels similar to what you have in JAL, or you get PC+4. Okay? So if the condition is true, we say that the branch is taken, which means that the PC will be updated with the label. If the branch is not taken, which means that the condition is not true, we're going to just continue with PC+4, okay? So the default is always PC+4. So the question is that I said that 1 extra bit for JALR is for passing some specific information. Yes, it's for when we are jumping to function pointers, they wanted to find some flags. They wanted to pass some flags. Again, this is like very advanced and not really relevant to the course. So that's why I'm not bothering you with the details. If you're really, really interested, you can go and read the manual for RISC-V, but I'm not recommending it. Okay. Any other questions? Cool. So, and then, of course, again, back to ALU operations, you might ask, oh, why we are not having greater than, and why we're only having greater equal, and all those things. And again, the answer to those is we want to have a minimal set of instructions that satisfy everything that we want. And this set of minimum is satisfying all those things. So you can have branch greater, but you have to basically do 2 things, for example, in order to get that. Okay. So this is kind of like, a compromise that we make in order to make things compact. Okay. And then the difference between the signed and unsigned version is that when we are doing the unsigned version, we are treating both RS1 and RS2 as 2 unsigned values, similar to the way that we did it for set less than, all those things. So the question is, when we are doing the base plus offset, how do we actually calculate that? That's a great question. And when we are actually getting to the implementation, you will see how do we do that. Yes, you can use the base, you can use the actual ALU. In some cases, we add like simple adder in our data paths to actually do that. Any other questions? Okay, so let's have a short break and then we're going to come back and talk about pseudo instructions. Yep.
Um, so I'm not exactly sure the role that hard, like why are you supposed to be equals 4? Because shouldn't be like giving you the address of where you just came from, like your previous location. So wouldn't that be p minus 4 or just p forward?
No, because when we are jumping, remember that you are jumping from PC.
Yeah.
Okay, so if you say PC, you're again gonna come back to call, and you. So the way it works is that you either have to say, whenever I'm returning, I'm gonna add 4 and then continue, or whenever I'm returning, I'm just gonna run whatever it says that address is. Okay. If you do the first one, then you can say PC. But typically the default is that you do the second one, which is saying, oh, whenever I'm jumping, I'm just gonna execute this no matter what. Does it make sense? So you're here. Let's see if it works. Okay. So you're in this instruction, let's say gel something, something, okay? And your PC currently is equal to 100, okay? So, and then let's say you're writing things to extend. So 2 options, right? Either I'm gonna save 100 to extend, and then I'm gonna jump somewhere, and at some point I'm gonna jump back. And if I jump back, it means that the PC is gonna be equal to 100, right? And then what happens after this? If I say, oh, I'm gonna execute this instruction again, it means that I'm gonna execute this instruction again. It means I'm gonna jump again, and this is an infinite loop. If I say no, whenever I'm returning, I'm gonna get the PC, but I'm gonna do PC plus 4, then that's it, right? To make things simple, what we say is that whenever I'm saving, I'm gonna save 100 plus 4. So whenever I'm returning, the PC becomes 100 plus 4, and then I just don't have to care about whether I need to add or not. I just continue. Yeah, obviously, right? So you don't want to do the same thing over and over again. Yeah.
Question about this statement. So I never saw an example of this. So is this something that the compiler does on its own?
Yeah.
So this is not something that this is not an option for us, right?
No. Yeah. If you put the label, yeah, it's not an option for you.
So
But in hardware,
it calculates the label that.
yes. Yeah. But for example, as I said, like there's going to be a question in your homework that we give you a label and we ask you for the immediate. So you have to actually calculate that.
So when you see the label, so the label is always like characters. So when you write
Yes.
there, it should be considered the offset.
Exactly.
Some point you mentioned like in some ISAs, like the program counter is actually available to the software. So is there like a security concern with that? Or like,
Yeah, you usually cannot read the PC if you're not like privileged. But if you do, then yes, there's a security. But that's the whole point with buffer overflows and all those things. Yeah. Yeah. Hey,
Yeah, you can, I don't know if you have it set up, but there's a way to connect this to that. And
I know.
compare.
Yeah. But then there is no way of record because I want to. I mean, I need my Zoom to record things anyway.
You recorded on this.
I can record it locally in this, and probably that's what I will do next time.
Yeah.
I try to use Wi-Fi from
Yeah.
projecting this to this doesn't work because the Wi-Fi sucks. So I need the cable to connect from here to here, and then use, for example, a QuickTime or something to record from here. But then I don't use the camera or.
So there's a way in Zoom to do it over the cable. So it'll pass from here to here through Zoom.
Yes.
I think. So then
But-
you just record.
But then again, this doesn't connect to Zoom because it's connected to Wi-Fi, and Wi-Fi on this doesn't work. the only way is that if I connect cable from here to here, and that will save the problem. HDMI to this.
Well, oh, you could do HDMI. Well, that wouldn't record unless you did a screen recording on that, but then you don't get your audio.
Yeah. Yeah.
Yeah.
No, with Wi-Fi, things get really problematic. I can do everything offline with this setup, with my own camera and all those things. It just, I don't want to do that. But next time I'll set it up anyway, because this doesn't work. I mean, the basic things in the university is that your Wi-Fi should work, right? So
I don't know what is up, because there was word that it was like the IP addresses that they ran out of them.
and it's just a local issue, because in my office, I mean, there are some hiccups, so it's not that bad. So I don't know.
It's super strange that this year it's just.
Yeah.
Well,
Yeah. All right, guys, let's continue. So quick things. Your homework is out, is on the website, so you can actually go in and check it out. You have until next Friday to answer it. Okay. There was another thing I wanted to mention. I don't remember. Anyway. So let's continue. Does anybody have any unanswered questions? Because we want to kind of switch gear and move on to the next topic. Okay. So great news for those of you who ask about sub-I and greater branch greater than and move. Somebody else asked about move and jump and all those things. So there's this extra feature in Rust 5 which called pseudo instructions. So pseudo instructions are exactly for the people who are coming from different ISAs and different backgrounds and really love to have their move and their jump and all those things, and they really don't like JAL and JALR and all those things. So pseudo instructions give you this capability of kind of like, you know, adding additional instructions to your set. What it does is that it doesn't really change the hardware. So it doesn't really add instructions to our instruction set. It doesn't change our hardware or the overhead and all those things. It's just, think about it as like an interpreter between your assembly language and your machine code, which your compiler understands this set of pseudo instructions. And what it does is basically replace it with these instructions that we talked about. So in other words, the pseudo instructions is things that you can use in your assembly code. But when it translates into machine code, it will translate into one or combination of instructions that is only supported on your base instructions. Okay. And again, it's only for convenience purposes. So it doesn't help you with performance. It's actually in most cases hurt your performance, because one instructions, turns into multiple instructions. But if it makes your life easier, you can use this pseudo instruction. So for example, if you have an instruction called load immediate. So for example, if you want to initialize a register with a value, you don't have to do, for example, add I x1, x0 and that number. You can say li your register and that number, and that's basically the same thing. So the compiler is intelligent and replace it with that. But if you feel like that you have to use li because ARM and MIPS use li, then you can use li. Okay. There is a whole bunch of these. And then actually this is kind of like, you know, the translation between li to what's really happening. Okay. So there's actually this list of pseudo instructions that we can use. There is, for example, the move instruction. There is jump instruction, as you just asked. There's call instructions. There's return instruction and all those things. There's branch greater and all those things, which basically what it does is that it will translate this internally before actually creating the machine code into a bunch of set of instructions that we discussed. Okay. And you're free to use this in your exams and quizzes and all those things, unless we say that you're not allowed to use pseudo instruction. So the question is that what happens really when we are writing this instruction, right? And the answer is that it might translate into one instruction, as I show you, for example, here. So li is basically an addi for us. So it's just 1 and 1. But in some cases, it's multiple instructions. Okay. So for example, jump is basically jalr with x0, right? Jal with x0. So it's still one instruction. But some of these, like branch greater than and all those things, they're actually multiple instructions. Yeah.
Are they similar to like macros? In something like C++ or
The question is, are they similar to macros? Some conceptually, kind of, but yeah, just think about it as it's giving you additional instruction without really having the hardware support for it. Because you cannot just say, oh, I really want this instruction. How about I adding it to my instruction set? Because adding it to instruction set has to go all the way in the hardware and be supported in the actual physical hardware, which is very, very expensive process, right? But what this does is telling you that, oh, what I can do is that I can provide this additional set of instructions that the compiler understands and can convert it to those lists of instructions that the hardware knows, okay? Again, this could be one or multiple. So the question is that the overhead to the number of instructions is like, you mean the translated one or? Uh-huh. Yeah, so if, for example, one pseudo instruction translated into multiple instructions, what happens in terms of performance? And the performance is hertz. So, I mean, yes, it's a negative thing. In most cases, it's only 1 or 2 instructions. And again, you're trading performance with convenience. And in some cases, that's very useful. So if, for example, saves time for a software developer to write a program much more faster, and then the amount of money you might save in your company might be higher. So that could be, for example, the trade-off that you're paying. Okay. Yeah.
What stage does this taken? I mean, when you write code, stuff like assemblies and now there's a new layer that the student instructions are generated to this instruction.
So the question is, at what point this translation happening? At the point that we call it the assembler, which we at the assembly level we still use pseudo instructions. At the machine code level, we just use the actual instructions. So at the assembler level, when we are translating our assembly code to machine code, this translation happening. More questions? So the question is that if the instructions are stored as 4 bytes, and then if these instructions are translated into 2 instructions, wouldn't that create confusion and problems with the hardware? The whole point is that this is never, so hardware never sees this. Hardware only sees those instructions that we know it can support. The assembly code, the compiler for the assembly, which we call assembler, will translate this into instructions. So if on the hardware side, we only see those things that we know we can support. We don't care about these pseudo instructions on all those things. When you're writing your program, you can use the pseudo instructions. When you're translating into machine code, which actually what matters in terms of hardware, you won't see this. Okay? Sure. So the question is why it's a separate step, because think about this as someone wants to look at the assembly code, and those people who was behind this, they wanted their moves and all those things. Because yes, in majority of the time you write things in C and you don't care about the assembly, right? You never see it. But there are performance critical things that you need to hand optimize, and that's where you actually use assembly. So there are actually, believe it or not, there are people who actually write assembly for their living, and those people use this, okay? Yeah. But yeah, for you, you just click compile, it will create your assembly, it will create your machine code, it will run. You never see whether it was, you may not even know whether this was RISC-V or MIPS or ARM or whatever it was, right? Yeah, from the software point of view, there's no difference. Okay. Very quickly talk about the return and call. So return and call are pseudo instructions. You can use them in your code if you want to. Call is basically nothing but the same as GL, right? And we typically save the GL into this specific register called RA, which is I think X10 or something. By the way, I'll show you this the table for so. For some weird reason, we also call this registers some other name. So for example, X10 is called RA or RS and all those things. And the difference, and this is for, again, for compatibility reasons with ARM and MIPS. So they wanted to use that and we call it that. But at the end of the day, you can use X0 to X31 and you're good. The call is just basically saying that we are saving specific, actually, let me show you that first. Okay, so X1 is actually RA, and we usually, this is kind of like, you know, an unwritten contract between the compiler and the operating system, that it always assumed that your return address is saved in X1. Okay, this is part of what's called a calling convention, which we basically say that if you want to, for example, call to another function, and we want to use some registers in that function, what register should we use? Because some of those registers were being used by the previous function. And if you start messing things up, we might overwrite things that we shouldn't, right? And for that reason, we are following this calling convention, which basically say that, for example, if you want to write things to your register, leave X1 alone because X1 is your return address always. Leave X2 alone as well because this is your stack pointer. And also X3 because this is your global pointer. What you can use is all these others in the bottom. Like you can use your temporary registers, this 3. You can use these 3 here. You can use all these function arguments and all those things, okay? So basically, this is a good practice. Doesn't mean that if you don't do this, you will create a problem. But if you, for example, decide to overwrite X1, just make sure that you save X1 somewhere in the memory first, then overwrite to X1, and then when you're done with it, just load X1 again, back again, and then return, okay? Because we are assuming that our return address is saved in X1, okay? And whenever we're gonna write your programs in your homeworks and quizzes, we also do the same. You have to assume that this convention, this set of rules has to be followed. Okay, does that make sense? Any questions? Cool. So basically your call, and by the way, I'll probably take a look at the names as well. So like T0, like X5 to X7 is T0 to T2, X28 to 31 is T3 to T6. This is just to make your life easier to say which are the temporary registers. In order to memorize, instead of memorizing X28, you will say T3 or T4, right? So this is kind of like to make things easier. All right, so going back up, which I was here, yeah. So call is basically just saying that, you know, your destination register is RA, which is X1. That's the only difference between call and JAL. And return is nothing but saying that we don't need to do any linking part. We can just ignore the linking part and we just need the jumping part, right? Because for return, you don't care about the next address. You just want to go back to wherever you were, right? And then it also use RA as the source. So it's like a GLR with RA as the RS1. So RS1 is equal to RA. Okay. If you go to this table and look at these numbers and go back to that table that we just discussed, you will find this the minor details. It's not too important to actually like try to memorize any of these. It's just have some basic idea that when we are talking about these pseudo instruction, what really matters. Okay. Okay. So this is your return and call. How about you guys actually do this practice and see what is the output value of x10 and x11 when we are returning from this function. So let's call this a function. And so we are starting from here. And the initial value for x10 and x11 is 5 and 3. And let's see if we can figure out what would be the final value once we are reaching to this point. Yeah, so label doesn't have any meaning, right? So it first execute this, then execute this, then this, then this. This is a branch instruction, and as you can see, it might jump back to here, or it might just continue, right? Anybody? $15 and 0. Anybody with different answer? Anybody can tell what this function basically does? It's a mathematical function. Which is multiply, right? This is a multiply function, right? Because it basically says just loop on x11 multiple times until it reaches to 0, and each time it's just adding x10 with itself, which is basically the definition of multiply, right? So if like x11 was like 100, we had to do this 100 times until we reach to the end. Okay, so this is like one simple way of implementing a multiply if we don't have the multiply instruction. All right, and this is of course is not the most efficient way, because if you want to multiply large numbers, it means that we have to execute this instruction many times. But it basically says that if we basically for your multiply, you need to execute 3 instructions in some sense, right? And for each time, 3 times of this instruction gives you the answer that you want, right? And anybody has any question about this specific example? Everybody clear why this is a multiply, right? Okay, move on. For some reason, we are very, very slow. All right, so I'm gonna just leave you guys to do this as your homework. And so this is basically the opposite of that. If you're given a C code, how you can create an assembly code. Just do it yourself, and I'll ask the TAs to also go over it in the discussion sessions. All right. If you have any questions, next session we can talk about. All right. So again, quickly about the calling convention. So when we are starting a new function, we need to follow a set of rules, right? For correctness, usually the rules that we need to follow when we are calling convention is basically when we are calling another function and executing another function. We have two players here, the callee and the caller, right? The callee is the function that we're gonna jump to, and the caller is the main function, for example, right? The callee will be the callee would be that function, and the caller is the main function, right? So the callee has to promise that it's not gonna mess up with some of the registers that are saved and reserved. And when we are calling, we also have to pay extreme attention to the return address, because if you lose the return address, we have no idea where we have to go back to, right? And when we are returning back, there's also a whole bunch of, frame pointer and the previous state of the stack that we need to also follow. I'm not going to intentionally go through the stack part because I think part of the CS33 already discussed this. And if you take some operating system course, we'll also talk about this. Here's the actual, details of the stack. Again, I'm going to just skip it, just read it for your own information. This table is going to be one thing that we're going to use generally when we are writing our assembly instructions, that try to not to use this save registers when you're writing your own functions. If you have question about like where should I store the return address, you go back and look at this table and you see, for example, X1 is the answer and so on and so forth. Okay, so from now on, if you want to write an assembly code, follow this table and follow the registers that you have to use for that. Like use the temporary registers and all those things. Okay. Any questions? Cool. Somebody asked early on about the different data types. So this is the answer to that. So like double for us is 8 bytes. Float is 4 bytes, void, the pointer is 4 bytes, and all those things. Okay, take a look at this table if you ever have a question about the size. And that's kind of it with the ISA side. Very quickly, I want to talk about the machine code because we're going to use it in your homework, and then I'm going to let you go. So we have our assembly, and now we understand all the different instructions and variables and the operands and the commands and all those things. Then what, right? So how do we translate from this to the actual hardware? And the answer to that is the hardware itself doesn't have no idea about these instructions, these characters, and the naming of them. The only thing that the machine understands is machine code, which is basically just a bunch of zeros and ones. So how do we translate from that to this? It basically goes through the process called assembler, which takes the assembly code and it generates what's called a binary code for us. And this binary is just zeros and ones. In order to create that, we use a table, okay? This table is a standard table as part of the ISA that, for example, it says that, oh, if you see an OR instruction, this is the table, this is different parts of the OR instruction we have to follow, okay? So basically, now what I'm going to do is going through this table and giving you some background of what this table is. RISC-V, what it does is that in order to make this table more manageable and more understandable, they say that all these instructions that we talked about, the ALUs, the memory part, the memories, the control flow, all of them categorized in 6 different types: the R type, I type, S type, B type, U type, and J type. And all of them follow this exact same format. So all the R types follow this format like this. What does this format says? It says that, remember I told you that this is 32 bits, right? It says that the first 7 bits going to be used as the opcode. What is the opcode? The opcode basically tells you what this instruction is. It tells you whether this is an add-I or an add. So basically a translation between these characters that we talked about. For example, we talked about add-I here. Sorry. We talked about ADI, we talked about SW, LW, and all those things. And you can see that all of them have a different number. This is just basically a one-to-one mapping between the instruction and some number, okay? And we call that opcode, okay? For example, the opcode for AND is 0110011, okay? This is just a mapping. It could be any other number. It's just, it has to be a one-to-one mapping, right? If AND is this number, any other instruction cannot be this number. That's very simple, okay? So the opcode is basically says that. Then you have a bunch of different things. So all of them have the opcode. So opcode is exactly the same for any type instruction that we have, and it's always 7 bits, okay? Why 7 bits? Because 2 to the power of 7 is enough to cover all the instructions that we want in RISC-V. Remember, I told you that if we added more instruction, we needed to pay more overhead. One of the overhead that we had to pay was making this opcode bigger. And since this is only 32 bits, it means that we have to like cut down in some of these other ones, right? So we cannot really go beyond some number for the opcode, okay? Then you will see that some of these instructions has the destination register, which is basically these 4 bytes here. Again, why 4 bytes? Sorry, 5 bytes, 5 bits, because we only have 32 registers. So 2 to the power of 5 is enough for showing all those numbers, okay? And as you can see, some of them do have RD and some of them don't, because, for example, for a store word, we didn't have an RD, so we don't need RD for that. Then we have RS1 here, we have RS2 here, and then rest of this is these immediates and this thing called funct3 and funct7, which I'm going to talk about later. But basically, all this table tells you is that for these different instructions, given that some of them needs an immediate, some of them needs an RD, some of them needs both RS1 and RS2, but some of them don't, we need to kind of like, you know, schedule this table to stay within the 32 bits, but kind of like, you know, move things around in order to get what we want, okay? So how exactly this translates into the instructions that we talked about, this is the giant table that you need to kind of like, you know, go through to see, oh, if I have an AND I instruction, what's really happening? So let's say, for example, go with something like LW. So if you look at the LW, you first of all see that this is the opcode, right? Then you see that LW, if you remember, need a destination register because we were reading something from the memory. So it actually has the RD. So for example, if it's X10, we have to write 10 here. If it's X15, we have to write 15 here, okay? So that question that you had, that what's the difference between using 2 different registers when it comes to the machine code, is that if you use the exact same load with the exact same address, but with different registers, this value here, this bits here will change, and that's the difference between the machine code from one load to another load. This table is in your mind, basically, right? So this in your mind. No. So the question is where this table is stored. So the assembler is basically this big switch case that goes through the opcode first. So it says that, oh, the first thing I need to do is parsing the opcode to first understand what this instruction is. Then based on that, it's going to jump into this big switch case that says, oh, this is a load. Oh, okay, so I need an RD, I need immediates, I need this and that and that. So and then you parse these one by one, okay? So it's basically a big program. And the interesting thing is that you're going to write this program actually as you're part of your project 1. So you're going to get very familiar with how to do that in your project. You have to parse this one by one and go through it, okay? So going back here, load, for example, use this 010 for its funct3. Next time I'm going to describe what funct3 is. And then it's going to use RS1 because, again, remember, load needed RS1 as the base. And then this is the immediate part. This is the offset part. And as you can see, for load specifically, we have only 12 bits of immediate. It's just it doesn't have enough room to put other immediates there. Okay, so the best you can do is that offset 1204 to whatever base you have, plus and minus 1204, and that's all you get from your offset. If you want to jump to another location, you have to first update your base, then change that offset. Okay, same story with the store word. The only difference is, as you can see, the difference between store word and load word is that you no longer need an RD. So the store word is actually using immediate here, but they actually use RS1 and RS2. Another thing that you will notice is that the immediates are kind of scattered everywhere. So it's not like, you have this big, nice chunk of immediates. Like, for example, for a store, first 5 bits are here. The rest are kind of here. So still you get 0 to 11, but this is kind of like in between of your instruction. Okay? And I recommend you to go through all of these and take a look at it. It's not something specific. It's just read through them and then you can actually then one-to-one mapping of this types to this type. So at the end of the day, you only have 6 different variety of this. And that's what you get from your machine code. Okay?